Samuelson talk about Hall algebras and Fukaya categories. And Tony's going to have some announcements after? No.
Nope.
Okay.
That's short. That's the announcement.
Yeah. Okay. Well, first I'd like to thank the organizers for organizing this nice conference and giving me the chance to speak. So I'll be talking about joint works, one with Ben Cooper and the other with Hugh Morton. And right, so here's the outline for what I'd like to talk about. So there's sort of four things I'd like to do. The first is to define the Hall algebra. And I'll do sort of a basic example computation in it. One way to think of the Hall algebra is as some type of decategorification. It's a little more complicated than the other kinds of decategorification, but I'll say what it is. Next, I'd like to talk about the Hall algebra of an elliptic curve and sort of some motivation for the next two parts. Third, I'll talk about the Fukaya category of a surface. And fourth, I'll talk about some computations in the Hall algebra of this category. Okay. Okay, so so the slides are a little full, but there's only 10 of them, so there's some balance. Okay, so what is the Hall algebra? So this is supposed to be an algebra that's associated to certain abelian categories. So the categories will need to satisfy some finitary conditions. So the abelian category is called finitary if the Hom sets and the x1s are always finite as sets. So that's a bit of a strange condition. One way that it can be satisfied is if they're vector spaces over a finite field that are finite dimensional. So for example, if you have a quiver without cycles, you can take the category of modules over the quiver. And if you're working over a finite field, then this category is finitary. So you can take its Hall algebra. So the algebra is defined, so sometimes you define algebras using generators and relations. The Hall algebra is defined by defining a product structure on a vector space. So we sort of know ahead of time it's non-zero. So we take the, let's see. There we go. So we take the vector space spanned by isomorphism classes of objects in the category, and we define a product. So the first formula is just saying the structure constants I'm writing is C, M, N, E. So if I want to multiply the classes of two objects, I get a sum over objects E, and the structure constants look like this. So CMNE is the number of submodules of E, so that the submodule is isomorphic to M, and the quotient is isomorphic to N. Okay, so you're summing over possible extensions of M by N, or N by M, whichever way. Okay. And this is some, by the finitary condition, this is a finite number. And by the finiteness for X, this is a finite sum. Okay. So I just want to make a remark that if you're more geometrically minded, you can rephrase this product as coming from a convolution product. So you can take the set of exact sequences in A, it projects onto pairs of objects where you project onto the source and the source and the quotient, and then there's another projection to the middle term. And you can rewrite this product as a convolution product using this diagram. So the finitary condition gives, you can, if you think of these as discrete sets, then you get these structure constants. And the finitary means that this is proper. This math is proper. Anyway, so you can take that as a black box if you want. So the moral is that, well, there's some definition, and then experimentally these Hall algebras tend to be interesting. So for example, Ringel proved that if you start with modules over a Finken type quiver, then the Hall algebra is the positive part of the quantum group. where Q is the number of elements in the finite field. And so all of you know that this is an interesting algebra. So one might expect that other Hall algebras are also interesting. And as a technical note, there exists a definition of Hall algebra for finitary triangulated categories. It's morally similar to this. The structure constants are rational numbers, but I don't want to go into it. Okay. So let me just do one example computation in a Hall algebra. Maybe I won't spend too much time. So this is just a reminder that this is the definition of the structure constants. So in the example, I'll take a quiver with, this quiver, 2 vertices, 1 arrow, and A will be the category of modules over it, over a finite field. I'll say E1 and E2 are the simple modules that are one-dimensional, supported over the first and second vertex, and M is the module that with the K on both vertices and the map of 1 between them. So you can check that Hom from E1 to M is 0, and that there's a short exact sequence like this, E2 to M to E1. So then you can use that to compute these products. So E2 times E1, I should sum over all extensions where E2 is a sub-object of E of M. Sorry. So by dimension counting, you can show that the only 2 possibilities for an extension of this form are M and the direct sum. So that shows that E2 times E1 is a linear combination of the direct sum of E1 and E2 and M. And for E1 times E2, well, E1 isn't a submodule of M, so this product is just some constant times E1 plus E2. Okay. And then both of these things have a unique submodule isomorphic to E. This shows all of these constants A, B, and C are 1, and this means the commutator of E2 and E1 is equal to M. Okay. So maybe that was a little fast, but the point is that in this case, this computation is really just linear algebra, and it's pretty straightforward. So the exercises prove the Serre relation. If you can solve this exercise, you've done something wrong, because as stated, it's not quite right. There are some cues you need to twist the product, and I haven't put them in. But you can see that like this type of computation is doable. Okay. So now I'd like to talk about the elliptic Hall algebra. So this is a much less doable computation. So in this case, we'll take x to be an smooth elliptic curve over a finite field, and E sub x, I'll write for the Hall algebra of coherent sheaves over this curve. Okay. And EQT is what's called the elliptic Hall algebra. I'm not going to define this because I won't need the definition, but Burban and Schiffmann defined this algebra by hand using generators and relations. And what they showed is that so there's these two there's the two algebras E sub x and E sub qt, and they showed there's a strong relationship between the two. So they said for any curve x, there exist complex numbers, so that if you specialize the elliptic Hall algebra to q equals sigma and t equals sigma bar, you get the elliptic Hall algebra of the curve. Okay. So the dependence of the Hall algebra on the curve x just comes through these two numbers associated to the curve. And sigma and sigma bar depend on the curve x, and they're actually the eigenvalues of the Frobenius operator on H1. And so they're really natural things. I don't need that for the talk, but they're natural. Okay. And this is a really hard theorem, and it's led to a lot of beautiful mathematics. So from the previous slide or two, you might guess that this should be an interesting algebra. And in fact, it is. So it's been related. So this paper was published in 2012. I think they posted it in 2005. So since then, there's been a lot of work relating this algebra to different parts of mathematics. So, and I've made a partial list, and also, well, yeah. So here's a list of some things. Each one of these could be a talk on its own, probably given by someone else. So it's been related to equivariant K-theory of Hilbert schemes. There's the Schiffmann and Vassereau showed that this algebra acts on that equivariant K-theory. In this action, using operators coming from this action, you can write a lot of conjectures in algebraic combinatorics and symmetric functions. There was a conference last week largely about this in Montreal. There's a family of bases of symmetric functions that interpolate between McDonald and Schur functions. That has very nice properties with respect to this algebra. This algebra is also related to triply graded homology of torus knots. So at least for positive torus knots, it was recently proved by Mellett that you can compute Betty numbers of this homology using this algebra, basically. And this builds on a number of conjectures. It's also related to the Q Heisenberg category defined by Gavanov and deformed by Licata and Savage. So roughly, this algebra is the trace of this category, roughly. And it's also related to the skein algebra of the torus. And I could make another slide with the list of more things, but I won't, or I didn't. So the point is that it's interesting. Okay. So I want to expand some on this very last point because it's some motivation for what I want to talk about later. Okay. So let me define the skein algebra. So given a three-manifold, you can look at the space formally spanned by links in the three-manifold, framed-oriented links, modulo these Hompley skein relations. I should have put the framing relation. I forgot to add that. Okay, so this is some vector space. If the three-manifold you start with has the form surface cross interval, then this vector space has an algebra structure on it, given by stacking in the interval direction. So here's an example of the product on the torus. So here's two curves. So P11 is this curve. The indices represent the homology class. So, and this is the commutator. So P11 times P01 minus the product in the other order. So this is the first term. And in this term, I put the P11 curve on top of the P01 curve. And then in the negative term, I put them in the other order. So P01 is on top. If you look next to this crossing, well, you can apply the skein relation to this difference, because that's the same as on this side. And you get this, which is Q minus Q inverse times this curve. And the homology class of this curve is 1, 2. Okay. So we get some algebra. And so Hugh and I described this algebra a little while ago. So we showed this relation is actually part of a family of relations that describe the algebra completely. So the statement is that for any x in z squared, we can define a generator. So I won't actually define it. It's a little bit subtle, finding the right ones. But there exist generators that satisfy these relations. So the commutator of p sub x with p sub y is supposed to be this constant times p of x plus y, where the constant is q to the d minus q to the minus d, and d is the determinant of this matrix here. Okay. So you can see this example relation is a special case of this one. So when these curves cross once, this is really just the skein relation. When d is more than 1, it's well, the curves cross a lot, and there's a lot of cancellation in this sum. So a priori you might think, well, for each crossing I need to switch each crossing, and the number of crossings is approximately d. And each time you switch a crossing you get 2 terms. So you might think that there would be approximately 2 to the d terms. But almost all of them cancel. That's just a very rough heuristic. And this type of cancellation is shown up in other contexts. Okay. Also I didn't put it on the slide, but this gives a presentation of this algebra. So not only do these satisfy these relations, but they generate the algebra, and that's all the relations you need in some sense. So one corollary of that is that this skein algebra is isomorphic to the elliptic Hall algebra in this specialization. So the elliptic Hall algebra has these 2 parameters, and if we specialize them to be equal, then the skein algebra is isomorphic to that. Okay. I maybe should point out that in this specialization, so I said these are the Frobenius eigenvalues. So the product, that was a slight lie. One of them is the inverse of the eigenvalue. So the product QT inverse is equal to the order of the field on this elliptic curve side. So this specialization is when the order of the field is 1. So that doesn't really make sense, but it's maybe amusing. Okay. Right. So our proof of this was sort of by brute force. We computed some relations and using earlier skein theoretic work of Hugh, and showed that there are enough relations, and showed that it gave an isomorphism with this algebra. But it's so the proof tells you why that the theorem is true, but it doesn't give sort of a moral explanation of why it's true. So this isomorphism between the skein algebra and the elliptic Hall algebra seems roughly analogous to a special case of mirror symmetry, Kontsevich mirror symmetry. So there's a big program relating invariance of certain complex varieties with a mirror symplectic manifold. So invariance on one side should be equivalent to invariance on the other. So the slightly more precise statement is that to a complex variety you can associate its derived category of coherent sheaves. To a symplectic manifold, one can associate the Fukaya category. Some people can. It's pretty complicated. And at least conjecturally, these 2 categories are the same. But X and Y it's not obvious at all how they're related. Okay. And in some cases, this has been proved. So the first example was by Polishuk and Zaslow in the mid-90s. So in that case, X was an elliptic curve over the complex numbers. Y was a topological torus with a symplectic form. So we know what the derived category of coherent sheaves is, but the Fukaya category, so very roughly, the objects are lines on the torus decorated by some representation of UN. And I won't say what morphisms are, etc. And so Polishuk and Zaslow showed that these 2 categories are equivalent. And the map that they used, well, so for example, it took a vector bundle E to some curve X. Oh, wait, sorry. Right, so E is a vector bundle over X. That object is a coherent sheaf, and it maps to some object in the Fukaya category. And the object it maps to is a line of slope given by the slope of E, which is some invariant of the vector bundle, decorated with some representation of UN. Okay. And in this isomorphism, something similar happens. So if a vector bundle gives you an element in the Hall algebra, elliptic Hall algebra, and that maps to an element in the skein algebra, which is roughly a line of slope slope E, roughly. Okay. So, I mean, you might, sort of morally, you might say, well, I can apply the Hall algebra on both sides of this thing and get this isomorphism. So there's a long list of reasons why that won't work, technical problems, that could fill at least a whole slide, probably more. But I won't go into them. I'll just say it's sort of roughly, if you were to take the Hall algebra on both sides, it looks a little bit like this isomorphism. So it's really just motivational, so I don't have to make a precise statement. So this leads to a couple of questions. So first, does this analogy make any sense at all? So one of the problems in trying to make this a precise statement would be that the Fukaya category has no a priori relation to the skein algebra. The only similarity is that objects in it look a little bit like elements in the skein algebra. For the rest of the talk, I'll try to sort of expand on that point a little bit and say that, well, so what is the Hall algebra of the Fukaya category of a surface, and is it related to the skein algebra? So from what I said before, this Hall algebra of the Fukaya category is likely to be interesting. And then this theorem gives us, this isomorphism gives us some hint of how we might try to describe this Hall algebra. And there's no complete theorem yet, but there's some progress, maybe. Okay. Any questions so far? Okay. Right. So next I'd like to talk about the Fukaya category of a surface. And there are several models for this. So it's we chose to use one which was defined by Hayden, Katsarkov, and Kontsevich. There's a number of other choices. We chose this one because it's basically a combinatorial definition. So, and it's defined over Z. So to take the Hall algebra, you need vector field, at least in this sort of naive sense, you need vector field, the base ring to be a finite field. So since this is defined over Z, we can reduce to F mod P. Okay. Right. So I want to make a precise statement, I'd like to go through this definition somewhat. It is a little bit involved. So maybe I'll go to the next slide and say the rough summary first. So the rough summary is that objects in this category are arcs on a surface. Morphisms are intersection points between arcs. And composition of morphisms comes from disks.
Arcs have got an end point or not?
Yeah. So these arcs have an endpoint. You can, so there are also objects that correspond to closed curves, but these, in their definition, these closed curves only come up in the homotopic category of twisted complexes or something. So they exist, but they take some work to construct, but they are there. But the basic objects, so there's sort of a combinatorial shell that's built out of the sort of combinatorics of the surface, and then you do this algebra, sort of fancy algebra to make the rest of the category. And in the sort of shell of simple things, the objects are arcs and not closed curves. Okay, so I'll talk some now about this Fukaya category. Right. Okay, so we'll start with a surface with boundary, and technically it's a manifold with corners. So there will be some corners on the boundary components. And we really want to apply the Hall algebra construction. We need a sort of a Z grading. So there's a way of grading homomorphism spaces in this Fukaya category using a foliation on the surface. So we'll start with a foliation on the surface, which is the section of the projectivization of the tangent bundle. So there's a line at every point. Curves can be graded. So a graded curve is, for each point on the curve, you pick a path from the foliation vector to the derivative of the curve. So there's these two vectors, and you pick a path in the projectivized tangent space at that point between those two vectors. And you do this in a continuous way as a function of time. So maybe one thing I should point out, a grading on a curve is determined by the choice of the grading at one point on the curve, by continuity. So if you pick a path at one point, then there's only one way to extend this path to all other points on the curve. So this might at first seem like a framing of a curve, but it's very different, actually. Okay. Now the point of that is, so there's also no canonical way to grade a curve, but it is a z torsor. So you can't identify the space of gradings of a curve with z canonically, but it is a torsor over z. So you can, if you have a graded curve, you can shift the curve by composing with an element in the fundamental group of the projectivized tangent space at each point. So shifting makes sense, and that's going to be the same thing as shifting in the derived category. Okay. So one point for this, one reason they define gradings in this way is that it allows you to define an intersection index of two curves that intersect at a point. So if you have two curves that intersect transversely at a point, there are three vectors in that tangent space. There's the foliation vector, there's alpha prime, beta prime, well, alpha prime and beta prime. So you can make a path from, so eta is the foliation, a path from eta to eta, where you go from eta to alpha prime using the grading of alpha, alpha prime to beta prime by rotating counterclockwise, and then from beta prime to eta using the inverse of this grading. Okay. So then that means you have a path from eta to eta, which you can identify as an element in this fundamental group, which is z. And we've oriented the surface so it's canonically an element in z and not up to plus or minus 1. Okay. So what I said on the next slide is that curves should be objects and morphisms should be intersection points. So here this intersection index is going to be the degree of the morphism corresponding to that intersection point. Another thing I should say, I didn't put it on the slide, but the grading you can sort of think of as an extension of an orientation. So an orientation is like a grading mod 2, roughly. So if you have two oriented curves, then there's an intersection index similar to this, which is valued in z mod 2. So the intersection is either positive or negative. It's a positive or negative crossing. Okay. So those are the sort of objects. Well, objects will be defined in terms of graded curves. Okay. So for the surface, so the surface always has boundary, and each boundary point will, each boundary component is broken up into some marked intervals. And the intervals make up this set which we write as M. These are the components of the marked intervals on the boundary, and the boundary is supposed to alternate marked, unmarked, marked, unmarked. Okay. And I said there's corners on the boundary, and those come at the intersection points of marked and unmarked intervals. Okay. So an arc will be an embedded graded curve in the surface whose endpoints are in the marked intervals. And we want the arcs to be not isotopic to a subset of M. So they go between two different marked, well, sorry. I'll leave it at that. So when I say arc, I mean an embedded graded curve whose endpoints are at M. And then an arc system is a way of, well, it's a choice of some arcs on the surface which are disjoint and pairwise non-isotopic. Okay. Okay. So a boundary path is something that's supposed to be a morphism in the category. So the category will be built out of a choice of surface, a marking for the surface, a foliation, and an arc system. So these arcs are all supposed to be disjoint. So what I said is that intersections are homomorphisms, but there aren't actually any intersections. So what actually happens is that if two arcs end on the same marked interval, then there's a homomorphism between them. So I'll say a boundary path is a curve that's contained in a marked interval between two arcs. And the surface should be to the right. Okay, so that's a lot of the sort of combinatorial things coming from surfaces that we need to define the category. Okay. So the definition, or part of the definition. So if we have a surface with whose boundary is broken up into marked intervals with a foliation and an arc system, then we can define this A infinity category. And I won't say what A infinity means, because I won't really need it for the purposes of this talk. Okay, so objects in this category are arcs in the arc system. Morphisms are boundary paths between arcs. So maybe I should draw a picture. So let me draw a disk with four, let's see. Okay, so this is a disk with 4 marked intervals. Let's say M is in yellow. Okay, and then I've chosen, so let's see, let me call these E1. Okay. So I'll say that I'll define an arc system, an arc system on the surface to be these edges, which are arcs from between AI and AI plus 1. Okay. So, so the objects in this category are the EIs, and then morphisms are going to be AIs. So there's a homomorphism, let's say, from E1 to E2 given by, so both of these arcs end on the same boundary marked interval, so there's a boundary path between them. And so hom from E, let's see, 1, so the arc, in the boundary path, the surface should lie to the right. So hom from E1 to E2 is spanned by A1, and hom from E2 to E1 is 0. Okay. So if you want to skip ahead a little bit, maybe just to the next slide. The next slide. This looks a little bit like what we were looking at for the quiver, the A1 quiver, except it would be true if we replaced hom with x1, right? Which we'll do on the next slide. Okay, but we'll get to that. So, so here's an example where, let's see, morphisms. So I gave an example of a couple morphism spaces. Maybe let me do one more. Let me draw another arc. Let's say X. Now I haven't said what the gradings are, and maybe I won't. But let's say this is X. Well, yes. So if I add this to the arc system, let's say I add it. Then there's a hom from E1 to X. and say a Hom from X to E4.
And is there still a Hom from E1 to E2?
Yes, there is. Yeah, good question. So boundary paths are allowed to cross other arcs. Yeah, let me, yeah, that's a good question. So let me give that a name, actually. Let me give this thing a name. So let's say this is C. So boundary path from E1 to X. So then this Hom space is K times C. Okay. So then the composition, oh, sorry. Okay, let me say there's a Hom from X to E2, and let's call that D. Let's say this is D. Okay. Okay. So composition of morphisms. So in an A infinity category, there's a lot, one composition for every natural number. But the interesting, well, the most important one is the 2, where if you want to combine two morphisms or compose two morphisms. So the composition is defined just by concatenating paths. So if we want to compose C with D, we get A1. So D followed, sorry, C followed by D is defined to be A1. Okay. So that's how to compose morphisms if they're adjacent. Sometimes that doesn't make sense. And if it doesn't make sense, the composition is defined to be 0. So for example, I could say, well, D goes from X to E2, and A2 goes from E2 to E3, but I can't compose the boundary paths, so their composition is just defined to be 0. So A2 composed with D is defined to be 0. Okay. Right? So, yeah. So it's an A infinity category. I should also tell you all of the compositions, but I won't. So mu1 is 0. Mu2 is defined using this rule of composition of boundary paths. And higher compositions are defined in terms of disks. But that's a little more complicated combinatorially, and I don't want to write the definition of A infinity category, so I won't. Okay. Any other questions? Okay, so let's look at an example. Oh, right, okay, so that's sort of this combinatorial shell of the Fukaya category, which is this A infinity category. And then to get the full category, you take the homotopy category of twisted complexes. And this is a triangulated category. Okay. Right, so one important thing that they did in this, or important for my purposes at least, in this HKK paper, so this is HKK, they constructed objects associated to arcs and closed curves, and either one of those can be decorated with a local system. And they construct these as twisted complexes. So for example, I didn't draw in this picture an arc from A2 to A4. And it doesn't exist in the combinatorial shell, but it does exist as a twisted complex and that's one thing that they construct. Okay. Right, so as I said before, the rough summary is that objects are these arcs, morphisms are these boundary paths or intersection points between arcs, and the composition comes from disks. Okay, so here's an example, which is the disk. So in this example, I'll say that the boundary of the disk has n marked intervals, and for the arc system A, I'll take n minus 1 of these arcs and nothing else. So I'm taking, in this example, it would mean I would take A to be E1, E2, and E3 and leave out E4 and leave out X. Okay. Then there are morphisms from EI to EI plus 1. All compositions of these morphisms vanish. There are no higher compositions for this choice of A. So in this example, the Fukaya category is actually an honest category. Okay. So let me just illustrate what this category is. It's pretty simple. So here's here's E1, A1, E2, A n minus 1, E n minus 1. Okay. And so this really is the Fukaya category I want to take is the sort of path category of this quiver. So the EIs are objects and the AIs are morphisms. And the composition is that AI plus 1 composed with AI is 0. Okay. So you can check that, so this looks like the A1 quiver, and it is, at least if you shift the degrees. So in the A1 quiver, the EIs are objects, and there's an X1 in between them. So there's a functor from this Fukaya category to the derived category of AN minus 1 quiver modules. So this is a typo, I should put dB here. That sends an object EI to a shift of a simple object in the quiver variety, the quiver category. And it's an equivalence, or derived equivalence. And this algebra, the Hall algebra of this category was computed explicitly by Hernandez and Leclerc. So we use this theorem to do computations. And maybe I should have included a description of this algebra. I didn't. But roughly, right, so we're taking the derived category of quiver modules. So I said for the abelian category of quiver modules, you should get UQ SLN plus for the Hall algebra. In this case, because of the derived part, you sort of get Z many copies of UQ SLN plus. And they satisfy some sort of nice commutation relations. So adjacent copies have an interesting relation, and far apart copies Q commute. Okay. So this is just a remark. So they also show this algebra can be realized as a K-theory of, or a Q-deformed K-theory of certain category associated to modules over the quantum loop group. I think this should be important, but I haven't yet really understood it. So I wanted to mention it, but I won't say anything more. I mean, what I wanted to point out is that it's realized as a Hall algebra and as K-theory of two different objects. Okay, so this gives an explicit description of this Hall algebra for the disk. Okay. And so we use this to sort of find some relations in the Hall algebra of the Fukaya category for other surfaces. Okay, so there's one more combinatorial thing I should say about surfaces, which is and graded curves. So if you have two graded curves that intersect at a point, you can resolve them sometimes to get another graded curve. And this resolution looks like a skein relation. So if these are curves, let's see, x and y, if these are graded, so I put the condition up there, there's a way to resolve them. Let's see. To a curve like this. Okay. Okay, so I said, let's see. So if the intersection index of these two curves is 0 or 1, let's see, I was a little imprecise there. So if this intersection is 1, intersection index is 1, then this resolution has a canonical grading. Okay. So if and you can sort of play around with gradings to convince yourself this is true. Yeah. Let's see. Right. So let me just do that actually. So let's say that eta is vertical, the vertical vector field. Okay. So let me just draw some vectors on these curves. Let's see. Yeah. Okay, so I want, so since these are lines, the tangent vector is constant. So what I want to do is rotate from x to eta like this, and rotate from eta to y like this. Okay. So that defines a grading of x and of y. And you can see that if I pull this down a little bit, I can, or wait a minute, is that right? Sorry, that's backwards. I want to rotate like this. Sorry. Yeah, this is always, okay. There, that's what I want. So if I pull this down a little bit, I can extend this grading to the resolution. And you can compute in this example that this intersection index is 1. And if the intersection index is 0, then you resolve the other way, and that curve resolution has a grading. Okay. Right, so what do we do? Well, we compute some relations, and they look like this. So let's assume we have two curves that are simple curves and graded, and that they intersect once transversely at some point in the surface. And there's a technical assumption we need, which is that endpoints of alpha and beta lie on 4 distinct intervals, 4 distinct marked intervals. So then the theorem that Ben Cooper and I proved is that in this situation there's a commutation relation in the Hall algebra that says that the commutator of these two curves is, well, a sine times q minus q inverse times their resolution, if they have a resolution, and 0 otherwise. Okay, so this is like a graded analog of the skein relation. So the commutator is like the skein relation on the left-hand side, and then this resolution is like the right-hand side, and the factor is the same too. Okay, and this sign is like in the skein relation, if you have a positive crossing, you get a plus on the right-hand side, and if you have a negative crossing, you get a minus, and that's what this sign is doing. Okay. So the proof strategy, we do some explicit computations in the disk with 4 marked points. I hope that wasn't me. Anyway, so Hernandez and Leclerc gave an explicit description of this algebra, and if you play enough with these Q-Jacobi relations, you can do this computation. And then these assumptions imply, so if I have these two curves, I can take a small neighborhood of them, and I get a disk with 4 marked points. And that disk embeds into this surface. And this assumption, this technical assumption, implies that this embedding is fully faithful. So that means there's an induced map on Hall algebras. And so this relation holds in the disk, and therefore holds in the surface. Okay. Right. So I wanted to Oh, well, before I do that, maybe I should make one comment. So one thing that still seems mysterious to me, this Fukaya category comes from physics in some way that I don't really understand because I don't really know any physics. But it comes from string theory in some way. And this skein relation, in principle, comes from Chern-Simons theory. But I don't know if those two things are related in physics or not. It would be nice if there was some physical explanation for why this is true, but I don't know. Okay. Another comment is that representations of this algebra, whatever it is, should be interesting, but they're hard to construct. One downside of the Hall algebra construction is that it's hard to construct modules. Usually you just get the algebra and you construct modules in some other way. Okay. So I wanted to give sort of one very concrete corollary of this. Okay, so I already said that if we start with a disk, then the Hall algebra, well, the Fukaya category is the derived category of the AN quiver. And in particular, it contains this UQSLN plus as a subalgebra, sort of in one fixed degree. And it's not so hard to show using a result of Brundon that so Lustig's PBW generators for this algebra UQSLN plus they map to these arcs in the Fukaya category, and you can define them sort of inductively. These PBW generators you can define inductively using Q commutators. And this skein relation here, if you work out the degrees right, it shows that, that it turns up as this commutation relation between the PBW generators. So here A, B, C, D are increasing. So let me just draw a picture of this situation. Oh, maybe I already did. So X here, X would be, in this notation, X would be E13, because it goes from A1 to A3. Okay. And then I could put in an arc here, which is Y. Let's call that Y. So then Y would be E24. Okay, so then this skein relation in the disk shows that these two X and Y satisfy this relation here. So that's the way that these indices work out. And yeah, and then you can work out other relations, and these all follow from computations in the, well, really in this Hernandez-Leclerc algebra. But they have a sort of nice interpretation in terms of the Fukaya category.
Some of these are Q commutators and some are ordinary commutators?
Yeah, exactly. So by Q, I mean the Q goes on the second term. And this is a Q commutator. This, yeah, if I didn't write the subscript, it's an honest commutator. Yeah. So this actually gives a PBW presentation of UQSLN plus.
Is your result suggesting that somehow, like, the algebraic analog of this mere symmetry is somehow like realizing the quantum group in just like the PBW versus? Although, yeah, in the Hall algebra you get the canonical basis, right? The normal Hall algebra approach.
Oh, you mean from the quivers?
Yeah.
Well, it depends on which. Let's see. Indecomposables in the Hall algebra for the quiver map to the PBW generator.
Oh, so you're getting PBW.
Yeah, it's something like projectives map to canonical or dual canonical or something. Yeah, so the indecomposables are these arcs in the Fukaya category. Yeah, so this presentation has appeared in the past. I don't know how well known it is. I mean, it wasn't known to me, for example. So I was, you know, I always thought these serrelations are kind of complicated, but written in this form, it actually is a pretty simple presentation. So and maybe these have natural interpretations in terms of some exact sequences in the categorification. Maybe, I don't know. And I wanted to end with something, some concrete formulas. Okay, so I'll stop here.
Any questions?
Could you just remind me of what in this context, what Q stood for?
Oh, yeah.
Is it order of a field, or is it?
Yeah, it is the order of a field. So what happens, at least for the disk, is that all the relations that you see involve Q in a polynomial way. So you can give at least for the disk, you can write a presentation of an algebra where Q is a formal parameter.
Yeah.
It's sort of like this whole, and then say if you specialize Q to be a prime, then it's isometric to this.
How are the category related when you change the arc system? You know something when you change A?
Oh, yeah. So if it actually, yeah. So they show that this category basically doesn't depend on A. So if you add an arc, then the two categories are Morita equivalent. And any two arc systems, well, okay. A could be empty and then you don't get much, for example. So if you have enough arcs, then the category basically doesn't depend on the choice of arcs.
In an explicit way?
It depends on what you mean by explicit. There's a natural functor if you add an arc, and well, it depends on what you mean by explicit. Uh-huh.
Is there a chance to get similar thing for Borel of other series?
Yeah, that I don't know. Yeah, that's a good question. I don't know if there's like a type D Fukaya category or something. It's possible, but I don't understand the construction well enough to make any kind of a guess. The physicists might be able to guess at least. Uh-huh.
So this map, is this a surjection or injection view?
Which map?
This map here? The generators map to the arcs and
Yeah. So in this Fukaya category, it's sort of Z graded. Well, it's not Z graded, but it has Z many copies of this UQSLN plus. So it's surjective. This map is surjective onto one copy of them. Yeah.
And one more.
Uh-huh.
Can you show us the slide for which this corollary follows from? Where was the statement of the theorem?
This one?
Where this?
Uh-huh.
Oh, yes, this one. Thank you.
Oh, yeah, sure. Yeah. So this relation here is this top relation here. So this EAC is an arc from A to C, and EBD is an arc from B to D. And since A, B, C, D are increasing, they intersect once, like this X and Y. And so the intersecting once means, if the degrees are right, that this commutator relation is true. Actually, all of these you can just check. You can prove directly once you're good enough friends with the Q-Jacobi relations.
We need to stop now because the next talk starts right at 2:30.
Okay.
So we'll have to wait any questions till the next coffee break.
Okay.